So I'm finally revising everything. Let's go. So first thing, alkenes and alkynes as well. This is the whole hydrocarbon chapter. Okay, let's see. So for alkenes, the length of the carbon-carbon bond is 1.53 angstrom. Yeah, these informations are not that necessary. Okay, the tetrahedral angle is 109.5 degree. That might be good. Okay. So more carbons in chain means more surface area of molecule, and that means more van der Waals forces. Yes, that looks correct. Which gives higher boiling and melting points. Okay. Oh yeah, there's that thing as well. So more branching, that gives less surface area, but it also gives closer molecular packing in solid state. So in solid state, you have more van der Waals forces, and in liquid state you have less van der Waals forces because of branching. So your boiling point uh, that increases. Wait. But closer molecules in solid state. So that means higher boiling point but lower melting point. Oh, it's opposite. Yeah, it's supposed to be higher melting point, right? Yes, because you will need more energy to break apart those interactions. So it should be higher melting point and lower boiling point. Okay, whatever. So 1 to 4, the first four members, which is methane, ethane, propane, butane, those are gases at room temperature. Then 5 to 17 you have liquids, and then you have solids, right? Alkanes are colorless. Well, alkenes and alkynes are also colorless. Generally all hydrocarbons are colorless. Only when you have uh, some other atoms attached to them will they actually get colored. Okay. Hydrogenation of alkenes and alkynes, that's one of the preparation methods of this thing. So yeah, just completely hydrogenate it with excess of H2. That's correct. Okay. Removal of X from Rx. So the first method for this is, okay, so it's metal acid reduction. Yes, right, this is a nice mechanism. Okay, fine. Words reaction. So this is used for symmetrical alkane generation and not for asymmetric. So if you have uh, R plus R dash, right, maybe that would give the thing that you want. Actually this is just one of the major products. There's also going to be all of the other things, right? Yes, yeah, that looks correct, right? So there's also going to be disproportionation, and yeah, RH will be generated and all that stuff. Yeah, that looks about right. Okay, next. Using hydride donors to kick out X minus. Okay, this seems reasonable. So this H minus is not actually present in the solution. It's basically like H minus. Whenever this AlH4 minus thing gets close to Rx, that hydrogen atom starts to behave like H minus. Though it's not like that in solution. It's not roaming freely. H minus never roams freely. It's very unstable. If it's in water, it will just react to form hydrogen and OH minus. Yes. Using carbon ion donors to kick out X minus. Okay, that's also correct. And yeah, R minus can exist in solution as a free species, so no problem with that. Clemmensen reduction. So this is one of the important points, that it cannot reduce COH group, right? It can reduce the ketone or the aldehyde, or if it's, yeah, it doesn't reduce the carboxylic acid. I don't know what mechanism it has and why it does the thing it does, but yeah, whatever. Okay, reduction of ROH, RCHO, RCOH using HI red phosphorus. So HI is a very something like a reducing agent, a moderate, I don't know, strong or moderate reducing agent. So basically you just have H radicals and H plus ions, uh, which do the whole reducing thing, and then the I minus ion just does SN2. So this is the mechanism. Yeah, that looks correct. Okay, then Hi is weak and can break homolytically to give H radical and R radical. Okay, so this is the one of the reactions where you do have H radical, right? Or it could be the other pathway where you have that uh, the substrate molecule. So for example RCI3 giving RCI2 radical and I radical. It could also be that thing, but it's okay to think that H radicals are getting created, right? Okay, and then this thing happens. Cool. So I2 is consumed by the red phosphorus to generate Hi. I don't know how that happens. So phosphorus gets, it must get so I2 it's going from, well, I is at least going from 0 oxidation state to -1 oxidation state, so that's reduction. So phosphorus should get oxidized, so maybe some kind of phosphorus acid will be generated, probably. Whatever, if you're not interested in that, all we need to know is that, yeah, this happens when you treat it with Hi red phosphorus. You will reduce thing, and also there's something like when you treat it with I2 and red phosphorus, it can get halogenated, actually iodinated. Yeah, right. So that's another thing that happens, but that's not in this note. It's in the next note, right? Okay, whatever. Oops, that's not what I wanted. Yeah, where was I? Soda lime decarboxylation. Soda lime decarboxylation. Right, this is a straightforward mechanism. The water is consumed by calcium oxide, okay, to keep this thing dry. So if you have water, this will become a reversible process, and we don't want that. So the main thing that makes this irreversible is the carbon dioxide that is released. So if there was water, then the carbon dioxide would be trapped and it would just form H2CO3, which is not good. So it's necessary for us to kill that H2O to liberate CO2, and that drives the reaction forward. Same thing happens in a lot of other reactions as well. The release of gases generally makes the whole reaction irreversible. Sometimes it is in equilibrium, yes, but that's only when you have like a closed container and then you are actually putting the gas inside to do something. Whatever. Next question. Coal based electro, oh yeah, this is the remaining part over there. So R minus Na, when you hydrolyze this thing, you get RH, and the remaining thing, yeah. Oh, in fact, you don't even need to hydrolyze this because the H is provided by NaHCO3. So yeah, that's nice, which makes sense because R minus is pretty unstable. So it's getting converted to HR and Na2CO3. That's much better, right? Okay, so that's nice. Then coal-based electrolytic decarboxylation. This is pretty straightforward, right? So this gives a lot of different products. The main one that we want is RR, and here too just removing the carbon dioxide, which drives the reaction forward. Okay, hydrolysis of carbides, that's also a reaction. I don't think it's a good option though, because really carbides not very commonly found. Okay, next, halogenation. So this is the reactions of alkanes. Okay, so free radical halogenation, pretty straightforward. Yeah. Okay, here are the important points. R radical stability determines the rate of the reaction and the measured product. So that makes sense. Bond energy, HF is more than HCl, HBr, and then HI. And so the main thing that matters is the bond energy. and these bonds being broken, those don't matter that much. So really, which one is the slow step over there? The initiation thing is not really a step in this mechanism for the long term. So in the propagation, which of them is the slow step? uh yeah, I think both the steps are the slow step, right? So the more stronger your bond hx, the stronger the hx bond is, better will it be. And the yeah, that probably makes sense. Oh, so okay, I get it. We are going from x2 to x. Okay, yes, that's correct. So you should also think about the rx bond, but that doesn't matter so much probably. So the second step should be the fast step, right? No, wait, no. The R radical generation, that will be the slow step. Yes, and that's why this is happening like that. That whichever has more HX bond energy, that will give. Okay, I don't know that much, but it looks sensible. Cool. So final result is that the reactivity is in this order: fluorine, chlorine, bromine, iodine. So that means fluorine will react with everything that it sees. So it majorly reacts with 1 degree, right? Because it's so reactive, the kinetically favorable product will be the one that's formed. Then for iodine, the thermodynamically favorable product are formed, which is the 3 degree. uh, yes, which is so, right. So this is when you have 1 degree, 2 degree, all kinds of hydrogens. So then iodine will react with 3 degree hydrogens, and then chlorine, bromine, they react with all three hydrogens, but in specific ratios. These might be important: 1 3.85, 182, 1600. So yeah, gives a rough idea that chlorine reacts almost the same with all the three hydrogens, and then bromine, it too reacts majorly with 3 degree. Okay, anyway, inhibitors like O2 decrease rate by forming undesired relatively stable species like ROO radical. Okay, that's okay. Nitration sulfonation. So it's radical mechanism. Truthfully, we don't know the mechanism yet. And by we, I mean I. I'm not searched enough about this. Anyway, but from whatever I did search, I found out that it is a radical mechanism. Yeah, whatever. So that happened. SO3 plus H2SO4. That's called fumic sulfuric acid. Okay. So H2H2O7. Oleum pyrosulfuric acid, disulfuric acid. This is the structure. There's also something called Marshall's acid, but that's not this. Okay, next. Oxidation. So it only works for 3 degree alkenes. Don't ask me the mechanism. I don't know. Combustion, not a big deal. Combustion is pretty. Yeah, in combustion it could be any kind of intermediate because high temperature, right? Okay. Initiate. Okay, isomerization. So yeah, isomerization only happens when you have a little bit of alkene impurity in the alkane, which generally is there. So treating it with catalytic amounts of H plus, that can basically isomerize the whole alkane thing. Yeah. So the propagation step is what matters. Basically, in the initiation step, you are generating the isomerized R dash thing, right? R dash cation, and then that thing takes the hydrogen from HR, and then the R plus thing, that, yeah, through rearrangement it becomes R dash plus, and then this keeps on happening. Termination not so important. Okay, yeah, so this termination gives this alcohol thing, but that's in very less quantity. The majority of the product is because of the propagation step. Okay, AlCl3 is used to consume Cl minus in case HCl is used for H plus, thus avoiding production of RX R dash X and complete use of alkene, as it won't be able to add HCl and become inert. Okay, that looks correct. Cool. So not just for the alkene adding Cl minus, it could also be that uh, this would get terminated because Cl minus, it is a charged nucleophile, so it will react with this thing that we have generated, right, in the propagation step, which is R plus and R dash plus. Those could also, yeah, that's I did say that. Fine. Alkenes. This is something important. uh, this angle beta is less than alpha because pi sigma repulsion is more than sigma sigma repulsion, so these deviate from 120 degrees. Okay, that's nice. Zaitsev's rule or Zaitsev rule or whatever. More substituted alkene is more stable because of hyperconjugation. So the thing is that hyperconjugation is the key thing over there. If there's no hyperconjugation, even if something is more substituted, it could be less stable. Okay, and yeah, pi bonds are going to create dipole moments with other groups, right? So cis is more than trans. I don't know, maybe trans had zero dipole. Yeah, I think so. Okay, whatever, that doesn't matter. Thing is that cis has more dipole moment than trans. Correct. Okay, melting point and boiling point are similar to alkene. Fine. Surface area, trans is less than cis. Okay, so cis has more surface area and trans is also more closely packed. Okay, that makes sense. Fine. Polarity increases boiling point. Okay, cool. Next. Wait, if polarity increases boiling point, then that means cis will increase the boiling point. Right, the boiling point, not the melting point. Yes, that makes sense. Cool, and that also makes yeah, it is in agreement with the fact that surface area of cis is bigger, and also it has more polarity. So in both ways, it will increase the boiling point. Okay. Partial hydrogenation. Basically, the last catalyst, it says this thing, and yes, this does partial hydrogenation. It reduces the reactivity of H2. There's also something called Rosemond's catalyst, but that's not for alkyne hydrogenation. It's for something else, I think. Okay, whatever. Next, anti-hydrogenation of alkyne. So liquid NH3 and alkali metal, that does it. Here's the mechanism. Right, the mechanism is long and boring. So it's just a radical and ion, a radical and ion thing, right? This won't work for terminal alkyne because right, it behaves like an like acid. Okay, next, halogenation with Zn. Right, so first the zinc inserts itself inside the alkyl halide, and then you have something like E1. Yeah, something like E1 mechanism. I'm not sure what it is. Okay, next, dehalogenation with I minus in aprotic solvent. Okay, so the stereochemistry is inverted over there. R2 R1 R1 R2. That makes sense. This reaction happens because of law of mass exchange, even though I minus is not a stronger nucleophile than X minus. Fine. And then what? Then you do E2 to keep this thing right. So yes, that makes sense. I2. Weird things keep on happening with iodine, right? Okay, next, dehydrohalogenation, E2 with a strong base. Right, so Hoffman elimination, that's when you have this N plus CH3 thrice thing. So it's a bulky group, right? For example, which means things which have bigger groups than this, they will obviously do Hoffman elimination. So it's done with OR minus generally, right? So alcoholic KOH, that's the main reagent for this thing. Okay, dehydration of alcohols, that's well known. Okay, but the thing is P2O5 and Al2O3, these also work. Okay, pyrolysis of ester. Nah, this doesn't look so important. Yeah, but have I seen this somewhere? No, I have not. Okay, anyway, so ester pyrolysis, let's just give something like that. Fine, I will keep that in mind, but it is not that applicable everywhere. Okay, Wetting reaction. This is a nice. This is a nice reaction. So this phosphonium halide, phosphorus halide. This reacts with the ketone, and it gives this thing. Okay. Coal-based electrolytic decarboxylation. Fine, this is well known. Reactions. Oh, wait. In fact, this was also for alkane, right? There it was a little different. Yeah, because there was just one carboxylic acid group on the whole chain, and it had to react with other chain in that case. Over here, that's not the thing. It can just form alkene. Yes. Next, dehydrogenation. Sorry, hydrogenation. Right. This is well known. In fact, this thing is not just for alkenes. It's also for acyl halides, I think. Yeah, those two have that weakness in the bond, like the CC pi bond is weak, and that's why it can do that. Similarly, the acyl chloride bond is weak, so it too does this. And in fact, the reverse of this process can be used for oxidation, right? So like oxidation of alcohols, that can be done like this. Okay, whatever. Next, well known, no big deal. It does anti-halogenation because alkenes are pretty reactive. Doesn't happen with aromatic systems because high activation energy. Okay, reaction with acids. This is the most useful thing, right? This is what alkenes generally do. Right. I think there's some rule that dictates where the E thing will go or the OH thing will go. I don't remember its name. It was something like Markovnikov. Yeah. Yes, it was Markovnikov. And it is changed when you treat it with peroxide. Oh, that's the next reaction, in fact. Yeah. So over there, the X radical first attaches. So that's a different situation in that case, right? In this thing, you have the H plus attaching. So the hydrogen first attaches, and in both cases you have an electrophilic intermediate. So in both cases, the intermediate will be more stable when the radical or the cation is 3 degree or 2 degree or more substituted in general, right? But the thing is that the order in which the H and the other species, X species or A species, reacts with it, those are different. That's why you have different rules. Okay, fine. So the peroxide is just catalyst. It's not in bulk. It's just used for the initiation. And after that is this X radical. So the X2, sorry, the HX is basically the actual reactant over there. Okay, cool. This looks cool. Okay, allylic substitution. Right. I've written a more general reaction over there, even though this might not have been necessary. But here's what happens: you have this Z radical generated initially, and then that propagates, right? So Y radicals are the unstable one over there. For example, Y could be hydrogen. So then Y will be the thing that gets attached to the, yeah, cool. That makes sense. Carbene addition. Fine. Okay, so for singlet, it just adds directly. Yes. So for singlet, the thing is that the electrons are in opposite spin, so they can directly add, because the electrons in the pi orbital of the alkene, those are also in opposite spin, so they can match up easily, and you'll just have two bonds. But for triplet, because of the maximum multiplicity rule, the electrons are initially in the same spin, so one of them will combine, but the other one, it has to wait. So it gives the intermediate some lifetime, and within that time this thing can rotate, so it gives all geometric isomers. Okay, epoxidation. So this MCPK thing, this is the most popular reagent for this thing, even though any acid peroxide can do this thing, right? So basically it's just for epoxidation. You don't really need to remember that it looks like this and it does all that stuff. All the useful stuff that it does is because of this thing that reacts, the pink and blue thing. Okay, this reaction needs aprotic solvents, as epoxide can react with protic solvents. Okay, fine. Yeah, I mean, like, epoxides are stable as a species, but they are not that stable that they will not react with the solvent. So epoxide can go through solvolysis, especially when you have H plus or OH minus, right? So basically epoxide is something like an ether, so it can do that. Addition of alkane. Oh, this is the nice thing over there. These are, now we're getting to polymerization, right? So initially you have this R5 plus generated, and that propagates like this. Yeah, that looks correct. Okay, polymerization. So this is the same thing, but instead of addition of alkane, you will have addition of alkene on the alkene, and that doesn't just stop there, it polymerizes completely. So H plus catalyzed, or it does not even necessarily need to be H plus, it's just any Lewis acid. Okay, any Lewis acid can do this thing. Okay, yeah, the mechanism is fun. Okay, radical mechanism. Radical initiators are used to initiate the process in the name. The propagation is similar. Okay, oxygen gas is an inhibitor and used to control the reactivity, allowing longer chains to form, right? Yeah, that makes sense. The more reactive the radicals will be, more will they try to combine with things, so they will react less selectively with the alkene. That makes sense. Okay, oxymercuration, demercuration. Fine. So oxymercuration, it's done by this Hg2 plus ion. Okay, and basically it's a solvolysis after that step, and then demercuration. So at first I didn't find the mechanism for demercuration, and I found this lately, right, when I searched again, and this is what happens. So the Hg plus, it first coordinates with this OAC thing. Oh, by the way, OAC, AC is for acyl group, and OAC, I think that would be acetyl group. Okay, right, from acetic acid. Okay, cool. So this thing Hg just coordinates with OAC, and then after that, yeah, OAC minus over there. then Hg and D combine, right? This D is just it should be H over there, but D. Okay, that's cool. And then this thing happens. So it's a radical mechanism in the end. Okay. Yeah. I wonder whether. Oh yeah. I forgot to say this, something like that. Actually, the step should be something like this over there. Here it should be NaBH4 or any hydride donor or any reducing agent, in fact. So any hydride donor, it will remove this OAC and put D over there. And then after that it does radical mechanism. Okay, cool. Then hydroboration, whatever. So BH3, it is actually present as B2H6, right? 8 dimerases because of its vacant orbital and stuff. Fine. See this bond over there, this BHB bond, that's actually a 3 center 2 electron bond. So it's actually just two BH3 molecules but combined in a very weird fashion that increases the stability but just makes it more complicated to understand, right? It's not a simple bond. It's actually just one complete bond with 3 centers, whatever. And this is called dipoling. Okay, so it reacts like this in a sense. Then this is not so useful unless you do something like this, oxidation. So hydroboration, right? You got hydroborated, and then you treat it with this peroxide conjugate base thing, and then there's a shift over there somewhere. Yes, this is the shift. So the CB bond changes to CO bond, right? So alkyl shift basically, and that gives this thing. And then after that, okay, so treating with H2O once again gives this thing. Actually I should have shown more things over there, because this oxygen B, what should be happening is that the oxygen will coordinate to B, and that will put a positive charge on the oxygen, and then after that solvolysis will take place actually, right? That's what happens. Cool. There's also hydroboration reduction, which I didn't show, but that also does work. Okay, so what was our original species? Oh shit, why did this happen all of a sudden? Where were we? So our original species was this thing, right? So for reduction, what should be happening? I think for reduction you just treat it with H2O, right? Yeah. So it should be generating some kind of anion, only then will this work. Probably what happens is that that should be happening, in fact. A BH3 reduction is correct, right? So instead of having R5 R6 over there, let R6 be hydrogen. Just put a solvent molecule coordinated to the boron, and then after that do a hydride shift. That will probably get it done, right? I mean, okay, it doesn't really matter, because in the end we know that after adding H2O, this thing just gives the alkane, and that would be hydroboration reduction. Then you have diol alders, and the more fascinating reaction is definitely hydroboration oxidation, diol alders reaction, right? So for this you need electron withdrawing and electron donating group, right? So for example, if on the alkene you have electron donating groups, then on the diene you must have electron withdrawing groups for the reaction to happen. Okay, ozonolysis, this is the important one, right? So the first step is very similar. You just form the ozonide, and the destruction of ozonide is what really is the thing, right? And this is going to get more complicated when you have alkyne, because there will be 3 bonds. But this is what happens. The ozonide attaches like this, and then after that, I don't know what gives this process, like why does this process happen the way it does, but it happens. Okay, it just does. And after that you have this ozonide, which has a peroxide bond, which is weak, and we can use that. In fact, yeah, I mean, like over here you have 2 peroxide bonds, and then now you have 1 peroxide bond that's probably more stable, so maybe that's why it happens. But still, okay, whatever. Next, destruction of ozonide form. So radical mechanism, just treat it with peroxide, right? Basically OH radicals that will do this thing. So it will regenerate the peroxide, and that's why it's radical, right? It's propagation basically. Okay, cool. So from this alkane, you just got this thing with the double bond, the double bond split, and oxygens put wherever it was split. Okay, then zinc destruction. Okay, cool. This is cool. Zn. Oh, by the way, this is a reducing agent, so these ketones will also be reduced to alcohols, in fact. Yeah, cool. Yeah, that looks correct. And then, I mean, it's not a reducing agent directly, but when you have zinc and water, that will probably work as a reducing agent, or maybe like zinc and acid. Yeah, that will be the best reducing agent you can have. So that will give alcohols, which is useful, right? That reaction is also useful, but this is the main thing that happens. H plus and other oxidizing agents. Yeah, so any Lewis acid, it will coordinate. Okay, after that this thing is going to happen, right? So the mechanism is not that important, because every time you're just getting this thing over there. Okay, so if hydrogen is there, okay, if hydrogen is there, then instead of breaking the carbon oxygen bond, you can break the carbon hydrogen bond, right? The main thing that happens is the breaking of peroxide bond and conversion into this thing. Yeah, so over there you have this acid, and it's basically oxidizing agents that we are dealing with, so maybe this thing will also be converted to an to something like an acid. Okay, cool. Okay, then H minus generally reducing. By H minus I should in fact be saying hydride donors, but come on, it's okay to think about it like that, right? So this mechanism is not the actual mechanism, but it's almost what happens, right? There will be more things than that, right? uh, it will be that, in fact, first of all your AlCl3 will coordinate, and then it will give your H minus, but let's just not show that. Yeah, that's what happens. Cool. So right, these ketones formed or aldehydes formed, they will be reduced to alcohols. Looks correct. H2, so the peroxide bond, that's why you can do that. Okay, and then after that, if you have even more H2 remaining, you can in fact do this. You can break the carbon oxygen bonds and form this thing. Cool. Oh yeah, so this diol thing is unstable, and it reacts to form this thing. Cool, that looks nice. Fine. So in the end, you just get alcohols. So any reducing agent will basically give you alcohols. It should also be the zinc over there that will give you alcohol, but whatever. Not necessary to show that. Okay. Hot KMnO4 or acidified KMnO4. The reaction of alkene with that. It attaches itself and then it does some kind of breakage. Okay. But it fine. So it gives MnO2 over there. And yeah. Cool. So what happens to the oxidation state though? It just did this thing and then right, so the charge on Mn, it didn't change, but you got that O minus over there. So it's actually MnO2 minus, but whatever. Okay, in case hydrogen is there. Okay, fine. So yeah, in case hydrogen is there, this aldehyde will be converted to carboxylic acid. Okay, cool. Next, cold KMnO4 or alkaline KMnO4 or OSO4, all of these, they will just do they will just break one bond and not all of them. So it's not cleavage, it's just hydroxylation. OSO4 is commonly employed for hydroxylation. It does not cleave. KMnO4, cold KMnO4, it can just hydroxylate and not cleave, but hot KMnO4 does cleave. Okay, right. So the mechanism is not that important. The results are okay. NHSO3 is used to reduce the remaining oxidizing agent. It is not involved in the mechanism. Fine. NHSO3, it is HSO3 basically H plus SO3 minus. I don't know how that is used to reduce. Yeah, whatever. I don't know. It's just some kind of acid. Why will it reduce? Wait a second. To reduce the remaining oxidizing agent is not involved in the mechanism. Okay, whatever. Maybe it is in fact involved. Maybe the hydrogen that this oxygen gains it's from NHSO3. Who knows? Anyway, the next thing, extended oxidation. Alcohol to carbonyl. Okay. So this is actually a reaction of alcohols, but whatever. It's okay to know it right now. So this is basically that one of the O minus, it grabs the hydrogen over there. That's the important step in the mechanism. So what happens is that the alcohol, it gets converted to ketone, and then the aldehyde can be converted to acid. Yeah. Cool. Looks nice, I think. Oh, by the way, it's not necessary that you should have that OH minus over there. It could also be that it just directly coordinates, right? So it's not necessary that it should be O minus. You can directly coordinate the oxygen's lone pair to the manganese atom, and that will also do it, right? So just open the pi bond of oxygen, that will do the thing, right? Okay, cool. And then you have Woodward hydroxylation. So okay, in fact it's not just Woodward, there's also Woodward Prevost hydroxylation methods, but it's only one of them, so it's fine, right? I mean, I have shown only one of them, there should be two. So I2, that gives this thing. It's not like that in the solution, okay? It's not like that. It is basically OI with a weak bond. It's not exactly like that in the solution. I plus, it does not exist in the solution. And then you treat it with the, yeah, so the usual addition that happens with alkenes, and then it does this thing, and then after that it does some kind of SN2, okay, breaking that away. Then you have this thing, and after that you treat it with H2O. Oh, so this blue step is this thing. You have this thing, with H2O you add this OH group over there, and then you shift the hydrogen, and then what is this? Oh, so you break that bond, okay. Huh. Why does it feel familiar all of a sudden? Yeah, whatever. It will also be through some other mechanism, right? So these coordinate, and then you have plus over there or something like that. Whatever. The end product is two hydroxyl groups in synth fashion. There's also the other way in which you could have it in anti fashion, but that's not covered in this note. It will be in some other note. Okay, alkynes. Okay, cool. Okay, dehydrohalogenation of alkenes. Fine. So it should be alkanes, because first you dehydrohalogenate to get an alkene, and then you dehydrohalogenate once again to get alkyne. So yeah, your starting material is generally alkanes. Vicinal halide alkanes, like vicinal alkyne, whatever that thing. Yeah, this is a weird mechanism. If it was something like E1CB, then it could have been better, but I guess, okay, this is also fine. But really, E1CB would have been much better as a mechanism for this thing. Okay, dehalogenation of alkene. Fine, just insertion and then the elimination step. Correct, this will also work. This also works, I think. Yes, right. Alkylation of terminal alkyne. So this I minus thing is basically NaI, right? So sodium iodide, that is used for this thing. Sodium iodide is something like a reducing agent. It gets oxidized itself to give I2 as a gas, and that drives the reaction forward. Okay. Alkylation of terminal alkyne. Mm-hmm. Fine. This is a nice reaction. It's right. This is very popular, I think, because I've seen a lot of questions on this. Okay, fourth, Kolbe's electrolysis. Fine. So now, so now you have an alkene, again alkene with the carboxyl groups. It's also the same thing. Hydrolysis of carbides. Then sixth you have, so hydrolysis of carbides, it can give all kinds of different things, all kinds of hydrocarbons, alkenes, alkynes, alkanes. Yes. Sixth you have this thing. I don't know what it's called, but yeah, this looks like a thing that could happen. Okay. Next, it's reactions. Halogenation, same as alkene. Okay, cool. Anti-hydrogenation. Okay. Yeah, so mechanism already discussed. Synhydrogenation. Synhydrogenation, it will be completely hydrogenated, or else you have to choose Lindlar's catalyst to reduce the reactivity of hydrogen. Okay, addition of acid, same as alkene. Cool, fine. The addition of acid, yeah, it's the same as alkene, except that I think the rate will be slower because you will have sp2 carbocation, which is not good. Okay, hydration. Okay, fine. Hydroporation. So hydration is basically the addition of H2O, right? So acid or base catalyzed. If it's terminal alkyne, don't make it base catalyzed because that will do that thing. So it's acid catalyzed generally, and it works. It works. The rate would be slower, but it will work, I think. Okay, hydroboration, same as alkene, fine. Hydroboration oxidation, same as alkene, except we get tautomerized products. Okay, cool. So we would have got alcohol for alkene. In this case, we will get enol. So that enol will tautomerize to give ketone. Reaction of terminal alkynes with carbonyl. Okay. Oh yeah, this is another thing. That's nice. Cool. So this is actually nucleophilic acyl addition. And if there's something else over there, so instead of R3 you have some leaving group, right? So some good leaving group, then the O minus, the negative charge on that would collapse, and you would get the leaving group kicked out, and you would form a oxygen carbon double bond, right? That would be SNAC, right? Nucleophilic substitution, but in acyl. Yeah, whatever. Next thing, oxidation to diketone. Yeah, looks correct. So if it was not for the third bond over there, this would have broken away, but it has a third bond. Okay, oxidation with alkaline cheminophore of non-terminal alkyne. Cool. So because it's alkaline, you have to treat with you have to react with non-terminal alkyne. So it gives this. Fine, looks about right. Okay, ozonolysis. By the way, this thing, it will pretty much just automerize directly. Yeah, whatever. Next, ozonolysis. Cool. So the ozonide over here, it's very bad looking. Fine. Yeah, this is the thing before the ozonide, and then it will change. Cool. And it still rotates because there's a sigma bond over there. In the previous case for alkenes, it was not bound by a sigma bond and it was free, so it could rearrange any way it want. But still, you have a sigma bond, so it still can do that. Okay, and then this thing happens, and we get the ozonide. And yeah, this thing is pretty strained. So unlike the ozonide form from alkene, this ozonide is unstable. So it just completely gets converted to this anhydride thing, and then from that anhydride you can hydrolyze it. So acid catalyzed or base catalyzed, both thing work, right? So it's just going to be SNAC all the time, and that gives this thing. Okay, cool. Cyclic polymerization. Just like Diel-Alders reaction, these two need extreme conditions or electron withdrawing or electron donating groups because of hydration. Right. This is a common question asked on exams. So that's nice. Oh, there's also something called aromatization of alkanes, which we have not covered, but it basically goes like this: that if you have a cyclic alkane and you treat it, and you use something like a copper rod and you heat it, and then you put the alkane inside it, all your hydrogens on the alkane, those will get converted to H2. So you have the hydrogenation of alkene thing. Yeah, basically that, but in reverse. And if you have a partially dehydrogenated alkane, then that's even better. So here's what I'm saying basically, that if you have this thing, right, and say it's already partially dehydrogenated, and then you don't want these hydrogens over there, you want to remove this. So what you do is that you put this with a metal surface, and then you heat it, and this will convert it to this thing, right, plus H2. So this H2 will be liberated, and that's the driving force for this reaction. This will be in an open condition, that's why H2 will be able to leave. When you have a closed container in which you are putting H2 and then you are heating it, it will basically form some kind of equilibrium, so you will not get the full product that, I mean the full percentage of product that you could have got. So do it in an open container, and that will give us this thing. That's whatever. That's aromatization. Yes, that's correct. Okay, that's it. That's it for this note. Let's go to the next note. The video is not ended yet. In fact, I should just take a break. So I will take a 5-minute break. Okay, I'm back. Arrive in alkyl halides preparation. Halogenation of hydrocarbons. So yeah, that's well known. Like alkene halogenation, that's the easiest, I think. You could also halogenate alkyne. Yeah, free radical halogenation for alkane, that will also work. Exchange of halogen. So if you already have an haloalkane, you can change it to something else. So the driving force for this reaction is the precipitation of Kx when X is not iodine. So when X is fluorine, chlorine, or bromine, right? In those cases, yeah, it just goes down. It precipitates. Okay. Same thing happens with AgF. So when it's not fluorine, it's chlorine, bromine, iodine, then it goes down, right? That looks cool. Fine. Next, halogenation of alcohols and ethers. Okay. So the first one is nice. The first one is very obvious. Yeah, you just use the H plus in the HX to make good leaving group, and then you do SN2 or SN1 depending on what conditions you have, and then you just get this thing. In case of MeOH, a catalyst ZnCl2 is used. Okay, cool. So for MeOH, you cannot do it directly because Me plus is not stable. So probably it's something like SN1 and SN2 combined, and when you don't have the SN1 path, we just have to do the SN2 one. So probably that's why you have less yield. Two pathways are always better than one, I think. Okay, so in case of MeOH, a catalyst ZnCl2 is used. Cool. ROH plus PX3. Okay, so PX3 can be used for halogenation, right? So it's basically because of the phosphorus accepting a lone pair, but in that process it kicks out the halogen. Cool. And then that halogen gets its revenge back by doing SN2 full. So red phosphorus plus halogen, that gives PX3, so we can use that as well. PX5, it also does the same reaction. Cool. ROH plus SOCl2, thionyl chloride. Yeah, it also goes to the same mechanism. The chlorine gets kicked out, and then from there it does that. Okay. Hey, wait, SOCl2, so there should be another chlorine over there. I forgot to draw it, but there's supposed to be another chlorine attached to sulfur. And then it does that thing. Cool. Seems about right. So just have that RCl, and the remaining stuff we don't care about. So this is an SN2 pathway. There's also an SNI pathway for this thing. So yeah, next. Yeah, this is another nice thing. So it's pretty much the same thing that you just have uh, whatever is happening over there. Where is it? Where is it? Yeah, in this thing, whatever is happening, you have the same reaction happening over there. But after whatever happened over there happens, you have this I minus doing E2 on this thing and generating I2. That I2 liberates as a gas, and then you treat with more HI, and then this thing happens, and then once again I minus, and it liberates, and then after a long time you will have this thing. Okay, next. So px5. Yeah, cool. That's nice, I think. Same thing happens for px3 as well, I think. Yeah, so this looks nice. So one halogen, you break the bond, you break the first bond, then another halogen and you break the second bond. Cool. Huns-Dicker's reaction, whatever that is. Ag and Br2 minus AgBr. Right. Oh, AgBr, that looks like something that might precipitate. Yeah. AgF doesn't precipitate, everything else does. Yes, 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 yes. Yeah. So what's happening over there? Actually, maybe it should be that AgF doesn't precipitate because we don't let it precipitate. We put a lot of AgF in the mixture already, so it's saturated with AgF. So the thing that is getting generated due to the reaction, that does precipitate because that thing is not saturated in that thing. Does that make sense? Right? So AgF, it is saturated in AgF. Solution is saturated in AgF. Solution is not saturated in AgCl, so AgCl might precipitate. AgBr will precipitate. It will be some kind of equilibrium, but the thing that we have put in the reaction mixture, that will saturate the reaction mixture and that won't precipitate back. Fine. Next. So what's happening over there is that you are forming an OBr bond, which is similar to a peroxide bond. It's weak, so it breaks, and okay, and then you have decarboxylation over there, and then RBr is formed. Hey, a similar thing I've seen somewhere else as well. Okay, I don't remember it clearly. This works because AgBr precipitates and CO2 also escapes. Cool. Nice. Okay, next question. Haloform formation. Okay. So first it behaves like a base to tautomerize the whole thing. Cool. And then when it's tautomerized, you will oh yeah, this is something that happens in phenol as well. So just like how phenol reacts with halogens, it's the same kind of thing. So the oxygen lone pairs is gonna, the oxygen negative charge, it collides, and then this carbon, that's actually the one that attacks the halogen, and that's why you have this thing. Okay, and then after that, hitting with OH minus once again, you once again automerize the whole thing, and repeating this sequence, you just have this thing generated, and then once again you hit with OH minus and you have this thing, and look at that, this CX3 guy, this is a good leaving group, but I mean it's a moderately good leaving group. So after that it's just SNAC mechanism and you just get this thing. Okay, and then it gets hydrolyzed. Yeah, that's obvious. Okay, then this thing CH3 and O2. plus. So CH3NO2, and in basic conditions, what's happening with this thing? Oh, it's still haloform reaction, right? Or is it something else now? So in OH minus it can do this thing. Okay. So because NO2, because NO2 can also tautomerize, right? So because CH3NO2 can also tautomerize, this too will show this haloform formation reaction. So the NO2 group, it can be removed and you can just have a CX3 HCX3 thing over there. Cool. NHNO3. Okay, that looks nice. Then next you have the reactions. So the first reaction is this. Huh. Right, I will keep that in mind. That, so for example, if you have DMSO, right, dimethyl sulfur oxide, that will do this reaction most likely. So O plus that X minus gets kicked out. Then after that it does something like this, and then after that, yeah, it just does this thing. Okay, so it what did it do? It oxidized the thing. It formed a ketone out of nowhere. This looks like a useful reaction because we can create ketones out of nowhere. Okay. So the oxygen is coming from the DMSO and this gets converted to DMS. Fine. This looks nice. Yeah. Yeah, that's correct. Okay, next. Boron oxidation. Once again, the same thing. Halogen gets kicked out. So this is a acyl chloride thing. Yeah. Yes, it's an acyl chloride, and that's why. Yeah. So the acyl chloride is actually pretty weak. The bond is very weak because it's polarized. So this oxygen, it can just attack over there, and then it is pretty much SNAC over there. So it does SNAC. X minus gets kicked out. Then X minus once again reacts with this. Cool. So then this gets kicked out, and then yeah. Huh. So what happened to this though? Wait, was that not the thing that we wanted to use? Okay. What? Oh, so we were just creating this actual intermediate species. Oh, okay. And this is just a spectator ion. Oh, that's weird. That's very weird. Fine. So then this is the one that will be used. So actually what we are doing is that we are reacting with an alcohol. So alcohol plus this species, that will give something like that. Right. Once again the X minus gets kicked out, and then OH over there. Yeah, that is how it's happening. Fine. I think there might be a different thing that would be happening, like oxygen, it would be coordinating its, yes, that should be happening. This is not correct. This is not correct. In fact, what should be happening is that, right, let's change this right now. Let's change this. You can't have two positive charges at the same time, right? So this will be R1, R2, X, and then this X minus is not yet released. Okay, what will happen is that this oxygen, it will provide its lone pair to that. So after that, boom, this just goes away, right? So after that, what happens is that this oxygen provides a lone pair to that, and that kicks out the X minus over there. uh, yeah, and its positive charge was already gone, so now you just have this positive charge over there. Cool. And then after that, yeah, after that, what it looks like, that's happening. Okay, so maybe it's not. Okay, wait, just wait. Something's off with this. Whatever, the mechanism doesn't really matter at this point. What matters is that you converted this to a ketone. Okay, so you can use this species, right? So for example, DMSO plus acyl chloride. Cool. And that will give us this intermediate, which we can use to oxidize the alcohol to a ketone. That looks nice. Okay, cool. Next, what is this? So oxygen gets excited to O2 star, which is basically this thing. It's like diradical. Fine. And then it reacts with halo form. Oh yeah, this is another important thing. So we know that halo form is like, no wait, halo form is poisonous because it converts to phosgene, not because of this reaction. Is halo form detrimental to environment? I don't know about that. Freons are okay, whatever, doesn't matter. The reaction is like this. So this H carbon bond, it splits, and this is going to form, you have a peroxide bond over there, so that's not stable. So this will happen. Okay, so that peroxide bond, that will basically kick out that chlorine over there, and that chlorine, that will basically form HOCl with this other OH. Okay, so just, yes, this is phosgene. This is phosgene, right? Yes, and then you convert it to this thing with some solvent to make it less poisonous. So this phosgene thing is poisonous, and that's why you should not ever use chloroform near animals, which includes us as well, right? So where do we have this oxygen diradical in our body? I don't know, but yeah, phosgene is a pretty not good thing. Okay, anyway, next question. Next section, words reaction. Okay, yeah, fine. uh, this thing, oh, so okay, this looks correct. Fine. I mean, AR radical is also not that bad. Come on. Actually, it is. Yeah, sp2, right? So it might be bad. Who knows? So then you are trading with you are using AR minus in that case, and that does ARSN to give this thing. Okay, looks correct. Carbene formation. Oh yeah, this is a very important thing. Whenever you treat something like this with a base, right, a strong base, that is, so HX but on the same carbon, then it can dehydrohalogenate to give yeah, so it could be even CB mechanism, or you could just directly do it to basically give this thing a singlet carbene. Okay, and carbene can be used to react. So for example, with NH2, right, RNH2, it will give this thing, right? So this is basically something like that is electrophilic, so it will just take the lone pair form from nitrogen, and then after that the reaction is very simple. Yeah, because it's negative charge over there. So next step is just proton transfer, and then after that you got this thing. So treating with it with a good base can do this thing, right? So it's just going to be E2 mechanism. Okay, and then treating with OH minus once again, that can get rid of that HX over there to give another carbene, Oh, and that will actually be, so this is how isonitrile groups can be generated. Looks nice, I think. Okay, next. Yeah, whatever this is. Okay, this also looks like the same reaction, just with a conjugated system. No, wait, this is a little different. Okay, this might be very important. So, what is this? This is called pyrrole, right? Yes, this is a pyrrole. So pyrrole reacts. Wait, but how come something that stable? Okay, it's also converting to something else, which is much more stable. Okay, fine. Fine. So pyrrole and carbene dihalogen thing, that can give us this thing. Okay, looks correct. Then you have some nomenclature at the end, that geminal dihalide is called dihalide, short form, and that's also called alkylidine halide. Okay, vicinal halide is called alkylene dihalide. Okay, and CH2X2 it's called methylene halide, even though it's actually a geminal halide, so it should be called like methylidine halide, but no, it's called methylene halide. I don't know. Okay, fine. So this reaction, I think I should spend more time on this. Okay, come on, this is easy to memorize, I think, right? So pyrrole or any system like that, right? Pyrrole, furan, something else, plus carbene with two halogens, that's a necessity. Okay, that will do this reaction, right? Hey, wait, this halogen over there, it was not really used. It was not used, so we could just replace it with something else, and maybe that also works. So yeah, okay. So like for example, if I replace this chlorine with R group, okay, so this will be, oops, less, very less. Okay, this is R, then this will be R as well. Okay, then over here you will also have R, and that will also have R over here. Cool. So instead of just chlorinating this thing, you could actually add any kind of group that you would want. There are probably electronic effects over there, but I think if I ever got some reaction like that, where instead of having CCl2 you have CClR, then this would be a possible pathway. Okay, next. Oh, so that's actually the end of this thing. Yeah, so the next one is not polymers, no, carbonyls. No, wait, first aromatic hydrocarbons, that's more important. Okay, once again, just give me a little break and I will start doing it, because this is a long one. Okay, aromatic hydrocarbons, let's do it. So EAS mechanism is well known. Cool. Next, orthopara directors for EAS in benzene. So the strongly activating ones are amine and alcohol thing. So phenol and aniline, they are strongly activating, even so strongly activating that they can directly react with halogens, right? They don't need a catalyst. Other aromatic systems do. Okay, so just activating are these things: amides, uh, carboxylic acid, but inverted. I don't know what it's called. OR. Okay, weakly activating, and then weakly deactivating. So still, halogen, even though it's weakly deactivating, it's an ortho-para director because lone pair resonance. Okay, CHX2, it is also ortho-para because hyperconjugation. NO, once again the same thing, lone pair resonance. So okay, this thing SOOH thing, yeah, so it's weakly deactivating, but at the same time it's fine. It's just normal resonance over there, I think, or maybe it could be lone pair resonance as well, but who knows. Okay, so these are weakly deactivating ortho-para directors. Then alkene, but with electron withdrawing groups. Cool. CH2 NR3 plus. Fine. So this is something I need to memorize. I'll do that later. First, let's just revise everything. Okay, meta directors. NR3 plus, then NO2, then CX3, then CN. Also, it's much bigger than CN. SO3H. Okay. So yeah, cyanide, SO3H, carboxylic acid, aldehydes. In fact, all kinds of carbonyl groups, those are generally deactivating, except that we saw that one. No, that's not a carbonyl group directly attached to it. It's oxygen that's directly attached. So that's why it's ortho directing. These are deactivating and meta directing. Okay. So yeah, carbonyl directly attached to aromatic system, that would be deactivating, meta directing. Same thing for cyanide, and yes, and then NR3 plus NO2 and CX3, those are strongly deactivating, and then mildly deactivating you have cyanide, SO3H, these groups. Cool. Different aromatic systems. Okay, solution is harder on ortho position than on para because of steric repulsion and SIR effect. Yeah, that's correct. So generally the para product is the one that's the most formed one, the major product. So it's hard to put substituents on ortho, but we can still do it by blocking the para position. So yeah, resonance structures with aromatic systems are better than ones without them. Cool. So instead of saying this thing, I should say that this contributes more because, right, because this benzene ring, it has two resonance structures, so this has overall more contribution than this thing, right? Yes. So how does this make it more stable though? Yeah, it's not making it more stable, it's just making it it's just increasing the number of resonance structures that you have. That would be it. Okay, next. On this basis, attack by electrophile on star position is better than on square position. This thing, this circle that I have drawn, this is just some kind of aromatic system. Okay, so on star position, if you attack, you will have positive charge over there, and then this will be positive over there. So 1 2 3 structures that don't interfere with the aromatic system. If you do it on the square one, you only have, oh, okay, so you got the positive charge over there. Yes, this is not correct. For the square one, that will be the positive charge over this directly interferes. Fine, and when it circulates and comes out, it's still disturbing the whole aromatic system, so it just doesn't work like that. Only one resonance structures where the aromatic system is not there, so the contribution of that structure is very less, right? So in general, you have the star position being better to attack than the square position. Cool. Similarly, attack on this black circle is better than star, which is better than square. Okay, cool. So it's always the same thing. Just find out when you have the system that least disturbs the aromatic systems formed, and that would be the best position to attack. Okay, this is called anthracene. This is called naphthalene, I think. I mean the actual thing with the two aromatic benzene kind of rings, that will be the naphthalene thing. Yeah, this is called naphthalene, I think. Correct. Wait, is that called naphthalene? I thought that in naphthalene you don't have this wait, what happened over there? You don't have this bond in between or something. Okay, whatever, we don't care about that. So whenever the resonance is in the peripheral ring, the outer ring, that works like a naphthalene ring. Okay, so electron withdrawing groups on the system make it less favorable to be attacked by E plus, and other systems without electron withdrawing group will be attacked. Okay, so in this thing, A and B are equally likely to be attacked, but when you put this NO2 group over there, which is a it's a deactivating group, then what will happen is that this B thing is now suddenly more reactive than A, because when you attack A, you have the positive charge on the ring, which is NO2, which is not good, and in case of B, you have the opposite, which is still not good because you have that NO2 over there, but it's slightly better than the other alternative. Bigger areninium ion length is preferable as long as it doesn't destroy aromaticity of already existing aromatic systems. Okay, that's nice. For example, in furan and thiopane, this star position is better than the square position. Yeah, because you got a bigger aromatic system over there. A bigger conjugated system over there. Yes, a bigger areninium ion basically. Yeah, and in case of the square, you have a smaller areninium ion. Yes. For pyrrole, this difference is negligible as nitrogen donates lone pair much more than oxygen and sulfur, thus causing more solution of the positive charge. All three are more reactive than benzene as lone pair donation is much more effective than pi bond resonance. Okay, that looks correct. Pyridine, on the other hand, is less reactive than benzene. Here there is no lone pair donation and nitrogen is more electronegative than carbon, which causes destabilization of positive charge. So pyridine less reactive, and okay, also plus charge on such directly on nitrogen atom is even more destabilizing. So electrophile attacks on star generally. Cool. So these are quinoline and isoquinoline. These are also less reactive than benzene. And E plus attacks on the ring without nitrogen to prevent areninium ion on the ring containing nitrogen. Okay. This is more important than preventing direct positive charge on nitrogen atom. Okay, fine. So what that means is that this star position and this circle position, those will be much better than the other ones, and over there too, the star and circle positions are better. Just that the sequence is changed because in one of them the positive charge is on nitrogen directly, in the other one it's not. Okay, next thing, different types of E plus. HSO3 plus, right? So sulfonation, basically it has this electrophile HSO3 plus. So you can also directly use H2SO4 plus SO3 mix, which is oleum or fuming sulfuric acid. Oh, and by the way, this is not actually a mix, it's not a mixture. It will give H2S2O7, which is actually called it's called pyrosulfuric acid. We just learned that. Okay, sulfonation is reversible, so adding SO3 will enable the side reaction. Okay, cool. Thus consuming H plus generated by EAS and shifting the equilibrium. Similarly, adding H plus will shift the equilibrium in reverse direction, that is known as desulfonation. So yeah, that's important. Desulfonation, because sulfonation is only one of the processes in EAS that is readily reversible. So you can sulfonate and you can desulfonate depending on what you have added in the reaction mixture. Cool. So just adding H plus will desulfonate the thing. SO3H is a deactivating group, so polysubstitution doesn't occur. HSO3 plus is a good leaving group, so we can substitute it by other electrophiles. Cool. By ARSN mechanism. ARHSO3 plus electrophile from EAS that gives ARE plus HSO3 plus. Yeah, fine. It is a bulky group. Due to all of the properties mentioned above, it is an excellent group for blocking the para and meta positions of monosubstituted benzene. Okay. Yeah, fine. NO2. So it can be reduced to NH3. So it's done with, once again, metal plus acid. That's the generic reducing agent for almost everything. So yeah, that reduces it to NH3. Uh, in this case, the metal that we use is tin, right? Sn. Next we have X plus. So X plus, it's not in the solution like X plus, but it behaves like X plus. So you need AlX3 or some other Lewis acid like that to activate the X2 such that it would react with it the way it did with alkenes. Well, not exactly like that. It goes through EAS. But yeah, you get it, right? It should react with the thing, but for that it needs extra instability, which is given by this thing, MXN. So this MXN is like ALX3 or FEX3 or something like that. And yeah, so pure metal plus halogen gas, that can also give us this thing. So just using the pure metal directly, that also works. You can also use HOX, that also works, right? The catalyst is necessary as aromatic systems don't react with X2 directly like alkenes. Iodination also needs an oxidizing agent to destroy the HI found on the side reaction. Okay, so for iodination you will have HI produced, which must be destroyed, otherwise it will basically be a reversible reaction in that case. So to destroy it, you need an oxidizing agent. Okay. Species like ICl can be used in place of iodine as they produce HCl instead of HI. Fine. So in that case you will have Cl minus, which is much better, right? Because it cannot reduce anything. R plus. So Friedel-Crafts alkylation. Okay, effectiveness of M for this reaction is aluminium, then iron, then boron, tin, zinc, yeah, all that stuff. If R x MXN minus, which is congruent to this thing, is polarized enough, then R plus can rearrange. This happens for when M is aluminium at room temperature. At higher temperatures, it is possible for other metals too. Oh yeah, I almost forgot this thing. So R plus, it can rearrange, and that's why Friedel-Crafts alkylation is not that good, and we use acylation in some other places where we can. So yeah, alkylation can give rearrangements. Cool. Yeah, so at room temperature it happens for aluminium, otherwise no, and for high temperatures it happens with all metals. So it's not just that this R plus is given through this one single reaction, it can be given through all different kinds of reactions. For example, ROH plus H plus, that behaves like R plus. Strained ring plus Lewis acid. Alkene plus acid. Yeah. Okay. Epoxide plus acid. Okay, so this thing, this opened thing, yeah, it doesn't actually exist. The epoxide never opens in the solution. It opens only when it has to react. R minus is an activating group, so polysubstitution occurs even when R plus is limiting reagent. To decrease this, we can take large concentration of aromatic substrate. Looks about right. Okay, then we have acylation. Cool. So COR is T2. Fine. So for acylation, you have. Wait. Yeah, this is actually acylation, right? So why didn't we write that anywhere? Okay, it doesn't even matter. So the usual way to do this is using a Lewis acid and acyl halide. And what else can you do? You can also, okay, fine. So you can also do this with ester. So it's very similar to hydrolysis of ester, except that you just use the intermediate to do ES. Okay. Oh, this is the actual anhydride hydrolysis. So this will also give us the same thing, and only this is used. The other thing is not. Okay. Then R, yeah, this also does the same thing. Cool. COR is deactivating, so polysubstitution doesn't occur. And then you also have this weird reaction. It's called decarbonation. So it can give you CO, carbon monoxide, and R plus. So you also have a bit of alkylation product. This reaction happens if R plus is very stable. So for example, Me3C plus, it's very stable. And for formylation, you would need this thing, right? So it's generated directly using carbon monoxide and HCl. Yeah. Okay, if COR group is a victim of SIR, then it becomes a good leaving group, as RC double bond O is stable enough. Thus, COR is not added at ortho position. For example, okay, that looks correct. Fine. This is not because COR is bulky, but because it exists as this in the solution. Oh yeah. Oh yeah. So the Lewis acid, we cannot use Friedel-Crafts reactions on aromatic systems which contain something that when you like for example aniline, right? You cannot do it with that because the Lewis acid will just coordinate with the nitrogen, and that will make it into a bad thing because it will be a deactivating group, so reaction won't happen. So yeah, that's important. Okay, and then what do you have? Wow, there are a lot of different electrophiles that you can use. You have RC double bond OH plus. Okay, cool. Fine. So what there, it will react with two phenols. Okay, fine. So this is for ketones. Hey, wait, where's that H over there? Oh yeah, there's supposed to be an H over there. RCH double bond OH plus, and over there is the H. Whatever, that should be there. So the aldehyde, it can react with two phenols. So I would guess that ketone, it reacts with only one phenol, right? Looks about right. Okay, next. RCHCl. Okay. How do we prepare this thing? So using this. NaCl. Okay. Hey, we know that this would actually just kind of go through SN1 to give aldehyde. So you are essentially just treating an aldehyde with acid. So that's actually the same reaction as what happened over there, right? So that will just give us this thing. Cool. Oh, we actually used aldehyde directly. Ah, that's why this happened. Fine. Cool. Okay, that looks nice. So, oh, so the OH is the one that's actually leaving. Fine, fine. Now this makes sense. Cool. So this might be in very small quantities, but it is acting as a reactive species. So yeah, that will do it. Okay, you also have this thing, cyanide. So how does this react? It reacts like this. Okay, forming an imine. Cool. Doesn't look that bad. Okay, then next you have this thing. What is this thing? R1 plus double bond Cr3x. Okay. What? Okay, fine. Yeah, how do you prepare this? So something like that, huh? Amide plus POX. Hey, have I seen this reaction somewhere? I don't know. But this looks like an important one. So we know that generally POX3 is just used to halogenate stuff, right? And by stuff I mean carbonyl and alcohol compounds. So in this case, it also does the same thing. It just uses the oxygen to. Oh wait, so the oxygen of the carbonyl is in fact used to attach. Ah, fine. It could also have been the opposite, right? No, it could not have been because it needs to kick out the X minuses. Only then will this reaction proceed. So it must be like this. Okay. And then it has that positive charge over there, and this does that thing. And okay, that looks correct. Fine. And then what? Okay. Okay, so that X minus over there, it combines with the carbon. Fine. And then what? It just breaks. It just breaks like that. Huh. I thought it would be a little different. I thought first of all it will like do something like lone pair donation. Yeah, it might have done that. Okay, so it just breaks and you get this thing. And then what? Oh, so that's the reactive species that we want. Cool. So POX3, it will create this reactive species when treated with that. So it's always the carbonyl oxygen that combines. Okay, that looks correct. Fine. And then what? Okay. Alright, fine. So this is a complicated reaction. Memorize this later. Okay. Let's revise everything else. HgOR. So the same thing is like oxymercuration, demercuration. Just using HgOR in this case. Cool. Hg plus OR. That plus EAS to give this thing. It just mercuration. Right. Okay, cool. Ah, yes. Diazium salts. These are one of the most useful things. So one way to generate this is by using NO2, right? Using HNO2 and some other acid, and basically yeah, this will give us nitrile. This will give us NO plus as the reactive species, and that will be the one that gives the next part of the reaction. So AR NH2 that will combine with NO plus to give this thing, right? So just a bunch of proton transfers and resonance that gives this thing. This is the diazonium salt. Okay, then S2O8. Ah, yes. This thing, no, this is also not Marshall's acid. It's something else. Wait a second. Oh, it is in fact Marshall's acid, but just the deprotonated form. Yeah. Okay. So that thing reacting with phenol. Cool. Okay, cool. So it just kicks out SO4 2 minus over there. So this must be like a very basic condition, only then will this happen. Okay. Right, so this is a peroxide bond over there. And that's why doing this. Okay, so then after that you treat it with H plus, so an acid quench. After this thing has happened, that will just give us another alcohol group over there. Hey, so much for just an alcohol group. You could have just treated with some kind of halogen and then some very strong base. Sorry, some very strong OH minus concentration. That would have done it, right? Okay, reactions with AROH, ARNH2, etc. Aniline doesn't react with RX MXN directly because of coordination between nitrogen and MXN, which makes the Lewis acid unavailable for RX or CROX. For RCOX. Similarly, phenol reacts to a very small extent. So this mechanism is a good way to make it happen. In absence of Lewis acid, these reactions happen to a very good extent as OH and NH are highly activating groups when not coordinated. ARCOOH also doesn't react due to the same reason and also because it is deactivating. Okay. So yeah, COOH, it also has that oxygen group over there, and that's why because of the same reason it doesn't react. And yeah, it's also deactivating. That's one of the reasons as well. Okay, that looks nice. Okay, different types of E for this reaction. So one reaction pathway is just treating with a base, forming this anion, and then doing with E. Okay, carbonyls. Okay, cool. Carbon dioxide, fine. So it's the same thing every time. Carbene. Okay, so carbene, prepare that by dehydrogenation and then do this thing. Okay, looks nice. And carbene, but with two hydrogens over there. Okay, fine. This does this kind of mechanism. Okay, cool. So haloalkane, yeah, so it reacts with almost any electrophile that you could get or anything that has a good leaving group. Okay, RRCX2, same kind of thing, it also reacts with that by kicking away the halogen. And then once it has done that, after that it will do it once again because another equivalent of base can be used to just take out the other halogen, and then that same base can be added from that carbon. Okay, so yeah, that's nice. So instead of just using OH minus, you could have also used OR minus, I guess. Yeah, whatever. RCX3 the same thing. So it's like, yeah, it's like the more X you have, the more will it get oxidized, because the more that base can attack from that carbon, the benzyl carbon. Oh, cool. CX4. Oh, so now all of them just halogens. Cool. So that just properly gives a carboxylic acid, right? It's the most oxidized one. Okay. Halogens, we can do it directly without phenolate. Yeah, that's also something. And that too without catalyst. So same thing happens for NO plus 2. It doesn't uh, it doesn't add to arenes, as it is not that reactive, but it adds to phenol and aniline. Thus, while in most arenes adding H, NO2 decreases rate of nitration as it consumes the H plus needed for the formation of NO2 plus from HNO3. In case of these compounds, wait. Oh yeah, NO2 plus, yes. In case of these compounds, it increases the rate as it adds to the ring, and then it is oxidized to nitro group by HNO3. These compounds suffer greatly from coordination of activating groups with the Lewis acid. So they are acylated to avoid protection. Okay. Then after EAS, they are deacylated. Cool. That looks nice. So this acylation is basically done to reduce the reactivity of that OH, so that it won't coordinate with the Lewis. Cool. These also show this reaction. Oh, this is called, I think, this is called Fry's rearrangement. Yeah. Yes. So when treated with H plus, it can do this thing. Cool. Attack on nitrogen or oxygen by electro. Okay. Cool. Attack on nitrogen or oxygen by E plus. Oh, so the thing before the Fry's rearrangement. Fine. So the most common one is this thing, the diazonium salt formation. Okay. The nucleophilic aromatic substitution reaction. Yeah. Yeah, this is another common pathway of doing it. Cool. So this is actually base catalyzed yeah, removal of stuff. Cool. SO32 minus. Fine. Sandmeyer's reaction. Right. These are some important things. Sandmeyer reaction. So let's go into the mechanism straight. So you have this diazonium salt. First you treat with copper plus halogen, right? So Cu2 plus ions basically, and that gets converted to Cu plus ion. In that process, it gives an electron to the nitrogen, right? So this is basically actually free radical mechanism. So you have this aryl radical thing, which is unstable, yes, because it's still sp2 and you have an electrophile, right? So it is still unstable, but not as unstable as as Ar plus ion. That would be really unstable, so still better. So, and after that it just combines with this thing. Okay, that looks about nice. Okay, and that finally gives this thing. Cool. Benzene reactions. Yes, so this happens when you have a really good base. So when the base is really strong, it can in fact do this thing, even if it's not a good nucleophile. Even if it's not a good nucleophile, it can create a path, right? So when the leaving group is not good, when nothing is going correctly, but you still have a hydrogen over there, you can treat it with a really strong base, and that will create a benzene bond, and then from that you can add nucleophile to that. A well-known base and nucleophile for this is NH2 minus. Okay. Also, it also works as a nucleophile in this case. Fine. Oxidation. So, yeah, just oxidation like that. Carbon-carbon bonds are also cleaved as if they were carbon-hydrogen bonds. At least one benzylic hydrogen is necessary for this. Alright, this looks nice. So benzylic oxidation, it just, yeah, it destroys everything. Base catalyzed desulfonation. Cool. So yeah, that's it. This was the thing. Okay, I'm gonna take another break. In fact, no, let's just end this video right here, because I still got to cover like 3 more things. So yeah, I will end this over here and I will do the other thing in the next video. Okay, see you guys later.